Right, so before we go and actually derive Leeson's equation, we need to consider exactly how an oscillator works, and so this is what we're going to do here in this video. So this is a block diagram of the feedback oscillator we're going to look at. So here is a sustaining amplifier. The output of the amplifier is fed out as the output of the oscillator. A proportion of this signal, Kf is the proportion, is fed back, and this goes through a resonator. Fr is the resonator function, and so this function has a gain of 1 at centre frequency, and it falls off from 1 in the normal way that a resonator does either side of centre frequency. So this signal is fed back to the input of the amplifier, and the signal is combined with broadband noise, white noise. So you may have thought of an oscillator as being a self-contained block that produces an output signal. Well, here we're looking at it a bit differently. Okay, this thing itself is completely self-contained. It has a noise source in it, but the noise is not really something we're terribly interested in. We know about that. That's just broadband noise. What we're actually analysing is this block here, which takes broadband noise and filters it with a very narrow filter such that we produce a narrow output spectrum. So the output spectrum is very narrow, as we know the output spectrum of an oscillator is, but we're suggesting is nothing more than filtered broadband noise. Right, so let's go and look at exactly how this loop works. So first of all, let's just consider very simplistically, if we didn't have an input here, then it is just a feedback loop, and we could say that for the system to oscillate, the gain would have to be 1 around the loop. We know that if the gain is less than 1, then the oscillations will exponentially decay, and if the gain is more than 1, then the oscillations will exponentially increase. So it must be exactly 1 in the absence of an input signal. But here we have got an input signal, and we know that the input signal will combine in phase with this signal coming back around the loop, within the bandwidth of the loop this is, because we've actually designed this oscillator so that this is positive feedback. So any input signal will be these two signals will add in phase within the bandwidth of the loop, of course. Right, so this signal here is not just the feedback, it's actually got the noise in it as well. The noise is actually in a practical oscillator is going to be very small compared with the feedback signal, but nevertheless this signal here is not just the feedback, it's got noise in it. Well, to consider what the loop gain actually is, the loop gain is the ratio of these two signals. So if we didn't have an input signal, then the loop gain is 1 because these two signals are equal. Well, now this signal is the combination of two signals, so we can see that the loop gain is going to be not exactly 1, it's going to be 0.9999 recurring, because this signal has got an input added to it. So the loop gain is very close to 1, but slightly less than 1. Now, this has an effect on the bandwidth of the loop. Negative feedback increases the bandwidth of an open loop system, and positive feedback reduces the bandwidth of an open loop system. And the ratio by which the bandwidth is changed is the ratio by which the gain is changed by the feedback. So in the case of this positive feedback, we have vastly changed the gain. In the absence of feedback, a very small noise input here would be amplified by the gain of this amplifier, and you still have a fairly small noise at the output. Possibly we might have 10 dBs gain or something like that. when we've got this positive feedback system, which is actually providing a massive gain, so we have a tiny noise input signal, which is much smaller than the feedback, and then ends up as being a big output signal. So we have a massive gain. Really, this positive feedback is in effect increasing the gain of the amplifier, and so we have a massive gain here. So we can see that the effect of the positive feedback is going to have a massive effect on the bandwidth. It's going to very vastly reduce the bandwidth. A way that this theoretical concept we've set up differs from practical oscillator is in linearity. A practical oscillator has limiting in it, which is very important to stabilize the amplitude. We all know that in practice you make an oscillator, and even if you don't intend to build any limiting in it purposely, the output is always stable. Because a practical oscillator has a very vast gain due to the positive feedback, it means that the tiniest amount of limiting has a very powerful effect on controlling the amplitude. But in this theoretical system we've got no method of doing this. So what we're intending to do is, hypothetically, we're going to imagine an AGC system which will, with a very long time constant, control of the gain of this amplifier to maintain a constant output. So that means we don't need to consider this in the simulation. We just know that this will be adjusted with a very long time constant, so it's stable for the period we're considering it, such that we get the right output level. So this means that the system is completely linear. Now we need to consider how this will differ from a practical oscillator. Well, it means that if we've got noise just coming in the input and passing through the system and being filtered and coming out the output, but we can look at this in terms of AM and PM sidebands around about a carrier. So it means that the AM and the PM sidebands will be processed identically. Now we know, or we're going to find out with this derivation, but we know from experience that the phase noise of an oscillator will fall off at minus 20 dBs per decade in the region that we're interested in, this derivation we're going to produce, whereas the amplitude noise of an oscillator will be flat. So this is what the phase noise does in the region we're interested in, and the amplitude noise is normally flat along the bottom here. But what it would appear with this this theoretical system we've got is that the amplitude and the phase noise would follow the same law, because they're going to be processed identically. Well, this of course seems rather strange if you think about it. We know with a practical oscillator that the amplitude is just stable, and what this is suggesting is that if we go down to very low offset frequencies, the amplitude is going all over the place. If we go down to very low offset frequencies, let's say a tenth of a hertz or a hundredth of a hertz, something very low, the phase noise is something that possibly we're not concerned with. But if the amplitude is going all over the place, this is something that we will notice, and we've never seen a practical oscillator do anything like this. So it appears that this theoretical model is perhaps going to behave very differently to a practical oscillator. Well, I've made some hardware to see actually whether a practical oscillator would actually do this, just to prove that if you build a practical oscillator that's completely linear, that it will actually have amplitude noise and phase noise that follows the same sort of law. Well, it's not very easy to make an oscillator do this, because, as I said, the limiting has a very powerful effect on stabilizing the amplitude, because in a normal oscillator the input signal is so small compared with the output signal. So in order to do this, you have to have an oscillator which has an extremely linear amplifier, and the amplifier is operated at a very low level, so the compression is minuscule, you have to have a very high noise level at the input, and you have to have a resonator with a very low Q. And if you do this, it is possible to make an oscillator with an AGC control that stabilizes the output, and then you can see that the amplitude and the phase follow the same sort of law. So here we have an oscillator, and in this plot here we're looking at over a fairly short time scale, so you can see it's 100 nanoseconds per division, so the frequency is something in the region of 10 megahertz, and you can see the amplitude is reasonably stable. If you look at the amplitude here, we're looking over a much longer time frame here. This is 50 microseconds per division, and you can see that really the amplitude is going all over the place. So normally an oscillator wouldn't do anything like this, of course. The amplitude would be stable, looking at it on an oscilloscope, no matter what time frame you look over. So we can't see this is exactly 20 dBs per decade, but we can see that with a linear oscillator that the very close in amplitude does fluctuate in the way that the close in phase noise does. Now, in the derivation of the Leeson equation that we're going to do in the next video, we're not concerned with the amplitude noise to carrier ratio, we're only concerned with the phase noise to carrier ratio. So how this theoretical model behaves in terms of the amplitude doesn't really matter. I just wanted to show you that the theory does fit with the practice. So what we're saying is that this theoretical model, as far as the phase noise is concerned, it will behave the same as a practical oscillator, but in terms of the amplitude noise it will behave differently. The amplitude noise won't be removed as it is in a practical oscillator. I should also say that some of the material I've had published with the Radio Society of Great Britain, but they were very courteous and said it was okay to reproduce it. That's quite convenient because with some things such as the measurements made on the linear AGC oscillator I've just shown you, the hardware I've scrapped now, and so it was a bit difficult to reproduce the measurements. The Radio Society of Great Britain are primarily an organisation for amateur radio enthusiasts, but there's all sorts of stuff on RF there that might be of interest to people. Now we will go and derive the Leeson equation in the next video. Thank you for watching.